Now that we know how to use congruent triangles to prove things, it's time for a history lesson. Many, many, many years ago, like 2,600 years ago, a man by the name of Thales Miletus is credited with discovering a way to measure the distance from shore to a ship. Ooh, scary stuff. He did this by standing in a tower and using a tool of his own device called a clinometer. Now, a clinometer is a very technical tool. It is comprised of two sticks nailed together, and the nail is used as a hinge. And what Thales would do is use this tool to sight down to look at the ship. And then he would turn his clinometer to someplace on the shore, and using that same angle, he would then find an object on the shore. And then he would measure the distance from the tower, the bottom of the tower, to that other object on the shore. And that was the distance to the ship. Why does this work, you ask? Well, let's look and see why. This is exactly what Thales did in order to show that his plan worked. Now, looking at our figure, that looks awfully complicated, so I'm going to simplify it a bit and turn the tower, the tree, and the ship into two triangles. And we know, because of the clinometer and the angle on the clinometer didn't change, that the two angles at the top of these triangles, the angles in the tower, are congruent. Okay? And because the tower height does not change regardless of whether we're looking at the ship or at the tree on the shore, it's congruent to itself by the reflexive property. And because we build buildings perpendicular to the ground, we know that the angles at the bottom of the tower are right angles. And of course, all right angles are congruent, so those angles at the bottom of the tower are also congruent to each other. Oh my gosh! Notice that we have two triangles, triangle TRS and triangle TRL, that are congruent to each other by the angle-side-angle postulate. Well, if those triangles are congruent, then their corresponding parts also have to be congruent. So segment RS is congruent to segment RL by the definition of congruent polygons, which means that the lengths are the same by definition of congruent segments. Ooh. And Thales of Miletus did this proof over 2,000 years ago. In fact, over 2,500 years ago. Now it's your turn. Take a look at this proof and see if you can find the errors. Go ahead and pause me for a bit while you look at it. When you're ready, press play again and I'll be waiting for you. You're back? Excellent. Let's see how well you've done. I'm hoping you didn't think the first two statements and reasons were in error because, well, they are indeed given. In fact, they're even marked on the figure already. And the third statement, we do have vertical angles here. And vertical angles are congruent. That's one of the theorems we learned back in Unit 2. However, if you got to this point and said, that's not right, you would be correct. Because notice that triangle KHL and triangle MHN, the order doesn't seem to match. Because notice that KH, segment KH, is congruent to segment NH. So when naming the triangles, those segments should be in corresponding parts or positions. So therefore, the correct statement on 4 is the fact that triangle KHL is congruent to triangle NHM. Did you notice that one? Notice the order of our congruent parts. We have a pair of congruent angles, another pair of congruent angles, but the pair of congruent sides is not included between the two angles. So it's not angle-side-angle postulate, it's the angle-angle-side theorem that proves that these triangles are congruent. And from there, everything else is correct. So if you guessed step 4, you are right. Now try a few more questions on your own, and then go to the next video.